Hi, I'm Auliya Tristan from the Department of Mathematics, Institut Teknologi Bandung. In this occasion, I would like to introduce my final project topic, that is the pricing the crypto option derivatives. These are the outlines of the presentation. Start from introduction, Monte Carlo pricing method, look-back options, and the last one is pricing models. Let's get into the first part. Introduction. A look-back option is an exotic option that gives the holder the right to buy or sell an asset at any price during a period until maturity. Using this option, a trader can exploit or hedge extreme movements in the underlying asset price. Look-back options can also help investors in reducing exposure to high volatility arising from extreme events such as geopolitical developments, pandemics such as COVID-19, or natural disaster. Until now, no analytical method has been found to determine the price of look-back options because of the payoff depends on the maximum and minimum price of the asset during a certain period. Therefore, a numerical method, that is the Monte Carlo method, is used to estimate the price at this option. The Monte Carlo simulation will be applied to price look-back options on the three pricing models that will be explained later. Monte Carlo pricing method. Monte Carlo simulation is a method used to estimate the possible outcomes of events that are difficult to predict due to the intervention of random variables. The simulation is a versatile model for pricing exotic derivatives for which a closed-form analytic solution does not exist. This graph presented the fundamental concept of look-back option pricing. First, the time period from 0 to t maturity time will be discretized into sub-intervals. Next step is using risk-neutral asset dynamical equation for crypto index to simulate the evolution of asset price, and then perform random simulation of asset price movement each time for a total of n time steps. Next, compute payoff at time maturity. Next, then discount it at risk-free interest rate. This step will be repeated by the number of paths. Finally, by averaging the discounted payoff for all paths, the price of the option will be obtained. Look-back options. There are two types of look-back options, that is fixed and floating look-back options. The following table depicts the payoff for each type, where uppercase M0T is the maximum asset values, K is the strike price, lowercase m0t is the minimum asset values, and then ST is the value at time maturity. We move on to the next part of this presentation, that is pricing models. The first model is Black-Scholes. The Black-Scholes model is the most widely used model for financial derivative pricing. A discretized asset dynamical equation for generating Monte Carlo simulation path can be expressed as the equation presented in the screen, where R is the risk-free rate of return, sigma is the annual volatility, and epsilon is the standard normal variables with mean 0 and variance 1. By looking at the equation, it can be noted that generating the asset evolution over time only requires one parameter to be estimated, that is sigma. For simulation, the factorized version of this equation will be used. The second model is an IG, or normal inverse Gaussian model. The NIG process is a 4-parameter distribution that captures skewness and kurtosis better than the normal distribution. These 4 parameters are alpha, the tail parameter, beta, the skewness parameter, mu, the location parameter, and then the last one is delta, the scale parameter. To generate the asset evolution over time, these 4 parameters need to be estimated from log return time series. The asset dynamical equation used in Monte Carlo for the NIG model is presented as can be seen in the screen, where M is the martingale correcting terms. Just like the Black-Scholes model, the factorized version of this equation will be used for a faster simulation. The last model that will be used is RFSV, or raw fractional stochastic volatility, with dynamics shown in the screen, where M is the real number, nu and alpha are positive parameters, W is the Brownian motion, W with the subscript of H is the fractional Brownian motion, and uppercase H in between 0 and 1 is the Hurst parameter. That's all for the introduction of my final project topic. What I'm gonna do next is modeling the estimation of parameters for all 3 models before doing the Monte Carlo simulation. Thank you.